All right, good morning, everybody, barely, and welcome to the last talk of the program. And it's a pleasure to have for this Amita Das. And in terms of Amita's history, she did her PhD at IIT Kanpur, then moved to the Institute for Plasma Research, where she was for a long time and did a great deal of interesting work on a variety of things. And she was known, I think, quite widely. She spent a year in San Diego in the late 90s. And then she moved to IIT Delhi, where she's now professor of physics, and she's been well recognized, a member of several Indian academies. And it's appropriate for this last workshop, this last talk in the workshop that, or the program, that we go out with a flash. And indeed we are. She's going to tell us about colliding surface waves and laser energy absorption. Please.
Thank you. Thank you. I thank all the organizers, Pat, David, Rahul, and all others to give me this opportunity. I would be talking about a new work that is ongoing. That's about colliding surface waves and how they enhance laser energy absorption in microglobule plasma targets. And in addition, I will also cover other novel mechanisms of laser energy absorption that our group has been working on. And so that's basically the title that it suggests. And the outline of my talk, the outline of my talk is, since there is a crowd of on fluid dynamics, and plasma is, there's a half of the crowd on plasma. So I'll give a brief introduction and a brief overview of conventional laser absorption scheme. Basically, you want that the plasma should get hot, and the way of heating is by radiation, and laser is a very easily available thing. So one wants to utilize laser to heat plasma, its species like electrons and ions. So there's I'll provide a brief overview of what the conventional mechanisms of laser energy absorption had been. And then I'll cover three aspects of our work. And if it doesn't get covered during the stipulated time, I can stop anytime. So the first thing is the ongoing work, as I had mentioned. And here I will talk about how closed microdroplet targets are very useful in enhancing the laser energy absorption, because the surfaces are closed, and the surface wave that gets excited and even the bulk wave that gets excited by the laser incident on it can collide, and the efficiency is found to increase. I will also be talking about the second part of my talk will be usually lasers are high frequency, so they couple very nicely with the lighter electron species of the plasma. So the energy transfer to ions are essentially a difficult thing, and which are very much required for fusion schemes. So usually the conventional scheme rely on two-step processes where the laser energy is transferred to electrons, and then the electrons transfer their energy to ions. This can be by usual collisional processes like Rutherford collision cross-section between electrons and ions, but that becomes inefficient when electron energy is very high. So people have, I mean, this is, community is still debating whether there are some anomalous mechanisms which can aid the transfer of energy from electrons to ions in an efficient manner. So this is one of the work that we carried out, and we showed that there's a possibility of such process through inhomogeneously because of the shock that can get formed in an inhomogeneous plasma. And the experiments at ILE, Osaka, and TFR, in fact, supported this. So that's the second part of my talk. In the third part, I have started this particular area after shifting to IIT Delhi. And here we look for direct energy transfer to ions without it being mediated through the electron species. Now, how can that happen? So if you impose very strong magnetic field of appropriate intensity, then electron motion can be constrained. And then the ions get coupled to the laser. And there are many interesting results in this regime that I could obtain, not only about absorption. We could show that the absorption in ion species, the energy absorption is more compared to electrons in the presence of magnetic field. We also came across some other very interesting results, which I will not have time to present. That's like efficient way of generating harmonics. And in fact, if you have very strong magnetic field, which are not present in laboratory these days, but perhaps will be operative in astrophysics context, we observe that plasma becomes absolutely transparent in the presence of strong magnetic field. In effect, if you have, and that is if the electric field is normal to the applied magnetic field, those radiative fields, for those the plasma becomes absolutely transparent. The species are participating in the dynamics, yet if you look at the dispersion relation, nothing happens. So effectively, in the presence of plasma, in the presence of strong magnetic field, plasma loses its collective behavior, and single particle effects dominate. This was another interesting result and may have implications in the astrophysics scenario. So plasma is like a fluid. So you can write the continuity equation and momentum equation for its different species. The species of electrons and ions, they have different masses. So you'll have two continuity equations. And the charge density and the current density can be written in this fashion. And each species obeys the momentum equation with the Lorentz force term. The pressure term can be there, and the collision with other species is also present. So if this term is very dominant, then one can forget these two terms. So in fact, even a hot plasma can be considered as a cold plasma. And that is the usual cold plasma approximations, that you ignore these in this pressure term in presence of this. And this fluid equation coupled to the Maxwell's equation then form the complete set. So for electron ion plasma, this will be a two fluid equation. If there are other species, then you can have more than two values of S. And there are a lot of simplifications which are possible. For instance, in the context of, because the electron and ion mass are very disparate. So in the context of astrophysics, often one one uses the MHD fluid model, which is a fluid model where the fluid velocity is essentially governed by the ion mass. The average just that are taken, the ion dominates there, and the current is decided by the electrons. So essentially, that simplifies this models considerably. But in the case of laser, it is just the opposite thing that happens. Here, electron dynamics is important. Ions are merely at rest, and they provide the neutralizing background. So the species that is active here is the electron species. Ion species are merely at rest because they cannot respond at such fast time scales. And then that is another model. When laser is present, this term will be important. But after the laser goes out, then there will be a time scale for which even this term can be dropped, and you are in the intermediate time scales where electron dynamics is dominant and ions are still at rest. And of course, later on, ions may also participate in the dynamics.
Question from someone who doesn't know the field. So in that case, the latter case you talk about, the electron dynamics is important. The ion will provide also a damping background, right? So your last term, USR times BS will damp the electron.
Yes, that can
sink for the
yes, yes. But if electrons are very energetic, the nu EI is very small.
Motive force on the ions from the fluctuating fields.
That will be there, but for the fast lasers that I'm talking about, the high power, ultra short, femtosecond, I mean the pulses, it may affect if it is a 40 times compared to the electron period. So that can also be affected. But usually the electrons are, and even in the ponderomotive force, if you look at it, okay, but the mass comes in the denominator.
I'm thinking of like linear turbulence,
yes.
Right? That basically the ions are coupled by the ponderomotive force of the high frequency plasma waves.
Yes.
So you're not worrying about that.
No, one takes into account. I have done.
But then the ions aren't just stationary.
They're not stationary if you have taken into account. So depending on the situation, in some cases, like the third problem that I have been doing, there these effects are very dominant. In fact, I have constrained the electrons. So that becomes a dominant thing. And because of the ponderomotive effects, I could get even more absorption. So it covers the entire time relationships. So I've already discussed this. And so how does a laser energy gets absorbed? If you have a single charge particle, then from an oscillating electric field, it cannot absorb energy unless there are collisions which it can encounter. Even if there's a pulse, laser pulse, even there, a single charge particle will, after the pulse goes on, it will be left with no energy. So what is responsible for this irreversible transfer of energy is essentially the collective behavior of the plasma. And the plasma permits many collective modes. And if you look at where you do not have any external magnetic fields applied to it, two of the dominant electron dynamics related modes are the electrostatic plasma waves and the electromagnetic mode. So here it is important to note, and this is the known omega p square is basically the square of plasma frequency, and it is related to the density and mass in this fashion. So higher the density, the frequency is high, and mass of electrons is small. So the electrons, so this is high for electrons. If you write the same expression for ions, it will be very small. So it should be noted here. So if you have an electromagnetic wave of frequency omega, which is less than omega p square, then k will be imaginary and it will not be able to enter the plasma. So there is a stop band, and only if the frequency of the electromagnetic wave is high, it can propagate inside the plasma. So this is the dispersion relation that it covers, and it can also be understood by realizing that essentially here, if you look at this equation, there is a displacement current and the conduction current. So the conduction current has a limit depending on density, and the maximum velocity a species can have is c. So high, but this at higher frequency, this can keep increasing. So there is up to the point where omega is less than omega PE, it cannot propagate, and later on, if the frequency is high, then it can propagate. Now, what are the conventional schemes of absorption so far? Because we realize the single particle effects single particle cannot absorb energy from the plasma. Essentially, they rely on transfer to electrons, and to ions, it is only a two-step process. It depends on collisional, or there is a debate in the community about collective anomalous processes. More or less, it is accepted, but then the debate goes on. How does the laser transfer its energy to electrons? Again, it can be collisional, but now there are also possibilities of resonances. Like it can resonantly excite plasma wave, and that plasma wave can the electrostatic wave can get broken up, just like the ocean waves we see here when we see the breaking of these ocean waves. As you can see, just like when they come to the shore, the amplitude of the waves get higher and they break, and the particles acquire energy. So similarly here, that happens. Then there are other two mechanisms which are known as vacuum heating and J cross B resonance heating. The dynamics there is also, the mechanism is also very simple here. In the vacuum heating, what happens is that you have a sudden surface, and this could be overdense plasma here. So when the laser falls at an oblique angle, and if the electric field is oscillating in the plane, then a component of electric field, which is normal to this, can extract electrons from the surface. And it is believed that these electrons, which are now in a combined field of electromagnetic wave, as well as their own collective fields, their trajectories become stochastic. And we have also shown in the symbol, I'll not be talking about that, indeed, that trajectories being chaotic. In fact, that was the selection of that which we worked, and we really found it. So that is one possibility how the vacuum heating takes place. The other is the same configuration, but here when the intensity of a laser is very high. Typically, if you look at the equation of motion, then the second part, V cross B by C in the CGS units, tells us that unless V is comparable to C, and V comes from the quiver velocity of the electrons of the plasma species. So unless that becomes, the intensity of the laser is in the relativistic domain, which for electrons, it will be 10 to the power 18 watts per centimeter square, sorry. And unless that becomes of that order, then the second term is effective. So when the second term is effective, you will have a J cross B heating, and even a normally incident laser with an electric field in this direction will excite quiver velocity of electrons, which gives rise to the J, which crossed with the B field of the laser can extract electrons here, and the same mechanism then works. So these were the conventionally known mechanisms. And so now let me come to the first part of my talk, where I can say that after the work, I got inspiration from this. Sometimes when you sit on the shore of a sea, you would have noticed that some waves unexpectedly come of very large amplitude, and you get wet by them. And that is all unexpected. So how does it happen? Randomly, it comes. And you wait and wait. And if you're waiting to encounter such a wave, it doesn't come. So I've noticed what happens is that there is a crust which comes in the shallow region, and then it gets wave broken, and then there is a return wave. And this return wave is of decreasing magnitude. if by the time the other crust from the sea surface comes and hits it, then there is a sudden higher amplitude of these, which gets generated by these colliding surface waves, and they come very deep inside, and the amplitude is very high. So let's see, we tried to capture such an incident here. Let me see if it, my student Animesh did this photography. So you can see he is pointing here. You should watch at this place. This is coming, and you see that it, there are two waves which crash, which collide, and then they crash violently. So something like this, that is the context of plasma to have efficient energy captured. This work is an ongoing simulations. It is being done with Dr. Animesh Sharma. He's a postdoc in my group. He has a very interesting background. He was a BTech in aerospace engineering, did his PhD from Purdue University, and 1 year postdoc from University of Illinois, Urbana-Champaign. For the last 1 year, he's learning simulation theory in my group. And he has basically done these simulations. So we have a closed target. We are looking for colliding surface wave if it's possible. In planar target, the surface wave generation itself is a matter of debate because you have to have an additional corrugation to have the additional wave number to get a surface plasmon kind of resonances. The curved target also helps when you have an incident laser beam and it hits here. So even if the electric field is normal here it will have a oblique component and it can extract electrons from it. The typical waist size of this laser pulse, in fact, was 19 micrometer. Here the radius or the diameter, I forget, was about 15 micrometer, 30, 60, and infinite slab he has done. He added a slight gradient in this at the outer ring surface. It was not sharp and for a purpose, but it doesn't matter. That's what we realized. The intensity was non-relativistic. This is if A0, which is the ratio of quiver velocity of the electrons to the speed of light. If A0 is greater than 1, then it is strongly relativistic. So this is the configuration for the simulation. The simulations were carried out with the Epoch platform, which is a particle in cell code, and that has been developed at Warwick, University of Warwick. The other very popular and very robust particle in cell code is the OSIRIS, which was developed as UCLA, and now UCLA and IST Lisbon are doing it. We do simulations using both of them, but this was done by Epoch. And the first slide had a slight cut off. I don't know by what reason. This is the results for 15 micrometer diameter. And this was the initial condition that I have shown you, the electron density. This is a movie, and you have to see. The blue colored electron particles will get extracted, and you will also see this is the average kinetic energy which is acquired by the electrons. And there's a red marker which will show how it evolves in time. So the laser has come, it hit the target. The electron flows here, you could see the Kelvin-Helmholtz instability. And then this oscillates. You can watch it again. There is a wave which comes here, and then there is a sudden burst of electrons here. Again, it comes back and there is a burst. And these peaks are correlated with the bursts that you observe this side and this side. So they are happening repeatedly, these collisions, and that is when the electrons are acquiring energy here. So one might say that if you increase the droplet size, this peak should come delayed. And indeed, that's what happens. First, okay, first let me tell you the electron energies that are gained. Almost up to thousands of keV electrons are observed in this case. And let's see this, yes. And we feel that this by using plasma microdroplets, the efficiency of absorption can be and you can see that at the time second, the ions also. These are the two blobs along which the electrons are extracted from the microdroplets, because here the electric field is exactly transverse like this. So at the center, it cannot pull out any electrons. It pulls out the side directions. And subsequently, the red colored ions also acquired that shape, while these electrons are through surface waves as well as the bulk waves, they keep colliding on the two sides of the target and boosting the energy of electrons. Ultimately, the structure of this droplet becomes something like a cup shaped here. So there were some experiments which had, you have a laser, there is always a pre-pulse to it. And for very high amplitude lasers, the pre-pulse comes almost a picosecond earlier, and that itself ionizes the droplet. And then in experiments, this structure becomes this, instead of a spherical drop, you will have this kind of structure. So they had done that. And when the main pulse comes, it extracts more electrons, and then things start to happen. But the experimentalists felt that this cup-shaped structure was of very high importance. And the small density plasma that generates here is important for having a 2-plasmon decay process, excite that. So these are electrostatic waves, and it is felt that by them that this in fact gives rise to energy absorption in the context of droplets. Yeah. But this is after picoseconds, and this exercise was not basically aimed at fusion things. Energetic electrons you also require for imaging and other purposes. So these experiments that were carried out at TFR Hyderabad, they were essentially meant for having as high energy electrons as possible. And there in fusion, you want to heat the ions. So I'll come in the third part about it. Okay. So, and they felt that it is because of the electrostatic wave, and that gets a wave broken. So we have difference in opinion. So we also did time FFT of the electric field that gets generated. It generates a lot of harmonics, 400 nanometer, 800 nanometer in incident laser pulse. And for the main signature of 2-plasmon decay is that you generate 3/2 harmonic of the incident laser, because it generates, I mean, it interacts with the original pulse and generates the 3/2 harmonic. That was the signature used by them to say that it's a plasmon decay. You can see its peak, it is very small. In the log scale also, it is, the harmonics are more prominent. So we do observe the signatures of that, but it's the colliding waves we feel, and the time correlation from that, we feel that that aspect is more important. In the Fourier space scale also, we see signatures of that, but that, it is there, the 2-plasmon process is also working at it, but it's not always like in reality, a lot of processes are at work. So we feel that the presence of that is also there, plus this particular effect, which we have identified, it's also of importance. So this is the ongoing simulations that we plan to continue, and it highlights the importance of closed surfaces, where you can excite surface and bulk waves and they would collide. So you can encourage the collisions. And it can be viewed similar to perhaps the earthquake, when the surface waves and the bulk waves try to just dissipate the energy, and the earthquake you feel at other regions of the earth also, which are very different, long distance away, the ocean waves and so on. The future plans in this direction is that we would like to have inhomogeneous droplets or oblique incident of lasers, non-symmetric targets, and then see how the surface wave propagates in a curved target structures. Usually, I mean, like I have, you all may know more, that if you have a concave surface of the target, then the surface waves get stagnated. And if you have a convex surface, they move faster, usually. I don't know how it may get related here. We have to explore and see. This was a 2D simulation. So we had carried, it's essentially a cylindrical target in 2D. Non-cylindrical and non-spherical targets. Even if we can have corrugated planar target, which can generate surface wave by the additional K vector, the surface corrugation that will provide. And if we use 2 lasers, will the colliding surface waves give rise to harmonic? So those are the questions we wish to explore in coming days. They have not done with different, they have not.
And I mean, to extend what you're doing, you're just referring to at the end, have you thought about tailoring the surface of the pellet, to optimize this process?
Yes.
I mean, one could imagine more than simply making a ripple, right? I mean, you want to say make a ripple of the right size and even the
yes
profile.
Yes. If that
so
can be optimal.
The moral equivalent of beach engineering.
Yeah.
Only here to make big ones rather than to get rid of big ones.
Yes. So if there are any questions, this is the second part of my talk. How much time do you have? 12 minutes.
Started at 11,
Okay.
but yet 20 at least.
20,
So
okay.
relax.
So this is the second part. If you have any questions on the first part, I can take that up, and then if not, then I'll start with the second part. So here, the point is that in the fusion case, you want to heat the fusion pellet. And what is observed in these experiments is that the compression of the fusion target is easy. But if you want to heat it up to ignition temperatures, that is the where one faces difficulty. So you can keep the target cool. And in fact, you would like to have the target cool while you are compressing it, because compression would be easier for a cold target compared to a hot target. So there are tailored laser pulses which can really compress the target. And then the idea is, and that's the fast ignition concept of fusion, that you send a very short, very high powered pulse from one side and hope that that will ignite the plasma, and the fusion wave then will take care of it. Now, since it's a compressed target, so if you send a laser, it's already an overdense target. So the laser cannot directly heat the ions or electrons. In fact, laser stops at the critical density surface, which is 10 to the power 22. It transfers its energy to electrons. These electrons are expected to move inside the target. And because it's a very high current which moves inside the target, and so plasma provides for return shielding current, which is of high density but low velocity. And then this combination of forward and return currents are unstable to several instabilities like Weibull, filamentation, etc. And one expects that the turbulence that gets generated will help in depositing the electrons, the energy of the electrons to ions. Because if typically the energy that is dumped on electrons, that higher MeV electron energy, the target size, the compressed target size is less than 50 micron or even 20 micron. Conventional schemes of energetic electron dumping on ions will not be possible, because then it shows that the electrons will cross the target and the electrons will not get stopped. So you want the electrons to stop inside the target and the energy to be taken up by the ions. So obviously, and there were some scaled down experiments at ILE Osaka which were saying that fusion happens because there were significant yields. So how do we understand it? So at that time, I was Sharad Yadav, we were working on an interesting problem where we had included density inhomogeneity for electron magnetohydrodynamics fluid model. And the equations were something like this. We were able to show that if you have, like, these are rotating electron currents in opposite direction forming dipoles. So one red is up magnetic field. This is a 2D simulation, and blue is down. And this dipole basically moves. Dipoles move. Monopoles are static. And if it encounters a density inhomogeneity of increasing gradient in this direction, then it basically gets squeezed up, as you can see here, and propagates inside. So these were different cases that we carried out. And you can see as it enters the high density region, it gets squeezed. These two lobes come together and they move faster also, some movies so. But when they come out of the high density region, they separate. So as these current structures enter the inhomogeneous density, they in fact squeeze, the lobes squeezed, and it generates shear layers. So, and at that time at ILE Osaka, this experiment was being done where they had a compressed core here, and then they were sending an ultra intense laser pulse. Now, if the timing of the sending of the ultra intense laser pulse was not proper after the right time, after the compressing it appropriately. So this is basically the laser axis. There are two electron spectrometers that they had kept it, one at 20-degree angles and the other is 40-degree angles. And when this ultra intense laser pulse was sent, these are the results that were obtained for electron energy. So it was, if it was at a right timing, which is 0 picosecond after compression, then you can see that at 20-degree ESM, this was the observation. These are the curves, this orange curves. Whereas at either later if you send or earlier you send, this is the electron that 20-degree ESM observes. Whereas if you look at the ESM at 40-degree, which is very side, this is the compressed core. So these electrons will only come through the corona, low density plasma, whereas this electron at 20-degree has to pass through the compressed high density core. There is no difference if it is being the ultra intensive pulse is sent later or earlier, you get the same energy. Whereas if you look at it at the right time, these electrons you are losing. These electrons of 15 MeV, which by coming here, are being stopped. So,
You're going to tell us about this anomalous resistivity mechanism?
yes. So they are getting stopped. So this is what we provided an understanding. So, yeah. This equation? So basically, if you look at G, the normal EMHD, you don't have this term. Low density is del square B minus B. And V is also related to curl of B because current. But now when you have a density gradient term, this happens, this is a very simple physics. What happens is that there is an additional drift which comes up. Additional drift, I forget now, this is either grad n cross B or something like that. So these dipoles, they're actually moving, but when they encounter the density inhomogeneity, this is grad n cross B, additional drift is there. Grad n is in this direction, and the direction of B is such that the two lobes, when they are going towards high density, they squeeze with each other. Whereas if they are going towards low density, these two black lines indicate the, it's like a top. Yes. Yes. No, we used, Sharad had written the LCPFCT code. So this was the result, that the lobes compress with each other as they go towards high density. In fact, you might say that this is a very approximate fluid model. But I couldn't find the reference while here, but just after a couple of years, there was a paper by Sergei Bulanov and his group. At that time, I was not working with PIC codes. My group didn't have that. So after that only I developed. So they had carried out PIC simulation and they also observed this effect and they had cited our work. So this was the first, this was a new thing that we had observed in this context. Now this is applicable to our understanding of the anomalous effect that I'm talking about. How do we understand that? If you look at those equations, in fact, the first, this is this term, and if you forget about the skin depth for some time, you can also get it in terms of Berger kind of equation. Those details I'm not providing, but I can, if somebody is interested, I can show the calculations. And one can write something like this. These are the collisional if they're present things. It can be either viscous or resistive dissipations. And here K is the density scale length, the typical value of density scale. So if, the Berger's equation also permits shock solution, and shock size is basically independent of the dissipative mechanism there. So even though your resistivity, the value of that may be very small, so no matter what small value it is, but this shock's width will adjust in a fashion that the energy dissipation will be the same. It will not be dependent on the value of the resistivity. That is a known thing. So then if you estimate that while traveling a distance of a density gradient, let's say all magnetic energy is stored, and which is observed in the PIC simulations, I'll show you. Then if this is like something like I square R heating, this is the energy dissipation. What is the energy dissipation rate? B square by 4 pi is the energy, let's say, in that. The radius of that filament would be pi a square in 3D. It's moving with the velocity of c. Electrons are moving with the velocity of c. So this is the energy dissipation rate. If you put, use the value of B using the Ampere's law, this can be related in this fashion, right? And that's, if you put it here, the value of B, you can find the value of R, which is essentially 1 by C, it is like 30 ohms. And the typical current that are observed in those experiments had the magnitude of 0.5 megaamps. Thus, electrons having energy, I mean, the voltage IV, and having energy up to 15 MeV can be stopped, and which is what is observed experimentally. So this, subsequently, we also carried out, this is a 2022 work. This earlier work was in 2029, New Journal of Physics. So we ourselves also carried out PIC simulations with a Japanese group. And there you can see that homogeneous, the dipole is, even after 25 picosecond, it is homogeneous plasma, it is not moving inside. But when you have inhomogeneous plasma, its axial velocity increases. There's a pinch that it experiences. And if you expand it and see, there are these regions, I don't know whether it's clear, but there are these Kelvin-Helmholtz and other instabilities which are coming up here. So, and you can see the energy loss. For the homogeneous case, it's so little, whereas the inhomogeneous case, there's this immediate loss of this energy, and magnetic energy gets decreased, kinetic energy of electrons rise. It's also seen in the velocity. There is a sudden increase in the velocity, and so on. So basically, this also, the PIC simulation, which doesn't have any approximations, our fluid model had approximations. So that also confirms it. So this is.
Is there a single shock, or is it more like shock turbulence?
Experiments, they cannot see the shock.
Okay.
It was just these diagnostics. So the third problem before I start is, how much time do you have? Okay. So before.
It's got at least like 15 minutes.
Okay. So if there are no questions on the second part, I can talk about the third part. So now here I am looking not at the two-step processes. I want that the laser should directly heat the ions without electrons coming in between. So what is the idea? You should constrain the motion of electrons, make them effectively heavy. How do you do it? You apply a magnetic field such that they just get tied. They acquire energy, but then they get tied. So they do not generate space charge and other things. And so we started out simulation. This was done in collaboration of several of my PhD students, and we have a lot of results in this, but a couple of things only I'll be able to present. So the electron motion should be constrained, and that is achieved by use of strong magnetic fields. And I will provide a glimpse of our work on magnetized plasma interaction with lasers. The condition that you constrain the motion of electrons, but not that of ions, is this, that the laser frequency should lie between the electron gyro radius and the ion gyro radius. So it should be less than the electron gyro radius. So in one laser cycle, electrons should be able to move several gyro periods, but ions, they are just free. They are not, they have not even completed one cycle. So that is the idea. So we carried out, several interesting results were observed, as I had already mentioned. If you have a magnetized plasma dispersion relation, then there are several passbands appear. So even if plasma is overdense, the electromagnetic wave can still propagate inside the plasma. So, and that depends, the dispersion relation also depends on the geometry, that whether the magnetic field is, the applied magnetic field is parallel to the laser magnetic field, or then there's something unique you get. If it is parallel to electric field, it's an ordinary mode, nothing will happen. One may presume so, but that doesn't happen because there are harmonic generation, different kind of things happen, which I'm not going to go through. And the applied magnetic field could also be in a direction of the K vector, propagation vector. Then you have the ECR and ICR, the electron cyclotron resonances and so on. So there are several passbands in the dispersion relation which now allow a wide variety of frequencies of electromagnetic wave to enter the plasma, and not only to propagate inside the plasma. There are several resonances and cutoffs. And so because of several resonances, there are new mechanisms of laser coupling energy directly to ions, which we have shown. And I think this part I'll be covering in detail. There's also a possibility of having a localized energy deposition by tailoring the density and B field profiles. We have shown that the efficiency of higher harmonic generation at a particular B field is high, so optimized values. And the last result that I talked about the transparency of plasma. Plasma loses its collective property in the presence of very high, strong magnetic fields. So this is the condition that we choose, and that implies that the magnetic field has to be much greater than this. If you look at this inequality. Now, what does that mean? If you have a lower value of laser frequency, then the B0 requirement will be less. And in fact, with the CO2 laser, which is the frequency is 10 times smaller compared to the conventional frequencies. So we have recently, there has been technological advancement where pulsed high-powered CO2 lasers are now available, which were earlier only continuous lasers. So if you take into account the CO2 lasers, then this comes out, this condition means that you require B0 of the order of few kilotesla. And at the moment, experimentally, it is possible to have 1.4 kilotesla. So we are in a regime where experiments in this particular regime can be performed in near future. So this will give rise to can open up a very new field of experimental research. Furthermore, there are also proposals now from various groups which talk about generating megatesla magnetic fields in lab. So that would, in fact, it will be well within this. And a lot of experiments can be done. So with this background, in fact, we had started this studying about this regime, and let me just constrain myself at the moment to the X mode dispersion relation. This is a magnetic field geometry where you have propagation direction, let's say, is in this direction. The laser electric field is in this direction, and magnetic field in this direction, and the applied magnetic field is also in this particular direction. In that case, the dispersion relation looks like this. So there, see, you can see at lower frequency also there are pass bands. This is the lower hybrid resonance where electrons and ions they move, they respond in same time scales. Electrons are magnetized, whereas ions are not. So this is the resonance happens at the boundary. And these are the other waves that we all are familiar of, compressional alphin and other things and so on. So this is the dispersion relation in this particular geometry. And so we carried out PIC simulations using Osiris and Epoch. So let's say we have a plasma slab here, and laser with non-relativistic intensity was chosen. The laser was incident normal to it. So since it's non-relativistic, the J cross beaming, we are ruling out all the conventional mechanisms first to show that this magnetized plasma, whatever is being done is by the magnetized plasma. So the incident laser is normal to this target since so vacuum heating is ruled out. And since its intensity is less than the relativistic, so even J cross B heating will not happen. So whatever happens is because of the magnetic field. Okay, so this configuration basically avoids vacuum heating and J cross B heating mechanisms. These were the simulation parameters, and we had limited resources. So we had taken ion to electron mass ratio as 25 in this particular runs, but now we have started using higher correct mass ratios also. So these are the basic parameters, and you can see without external magnetic field, the laser reflects. Here you can have different, optimize it, but there's something which goes inside, okay, in the presence of magnetic field. And that can be optimized, which we have done. So again, a comparison. Here, the surface, when you do not have any magnetic field, the entire surface, plane surface is pushed back, electrons and ions together, right? Whereas if you have external magnetic field, you can see the electron and ion density, there is a difference. And there is a wave-like structures which seems to propagate inside. So there is an electromagnetic wave which enters and generates electrostatic waves. So there, although the applied laser pulse had an EY electric field, but after entering into the plasma, it generates EX, which is this green lines. So electrostatic waves get generated, and their breaking, in fact, helps the irreversible transfer of laser energy into the plasma particles. So case B is the case with magnetic field, case A is without magnetic field. Again, you can see here EX generation for both the cases, and you can see that EX is more. The frequency spectrum, if you see, in the unmagnetized case, it's there are noises, and this is 2 orders of magnitude smaller power, and they are basically around the plasma frequency. Whereas in this particular case, they are around the lower hybrid wave, 0.2 value for this particular case. And there's a peak. The power is also very high compared to this. It is 2 orders of magnitude higher. And if we change the frequency, but keep it in the passband regime, so we are basically having this kind of frequency near the hybrid resonance. We changed it, so the frequency of these electrostatic disturbance doesn't change with different values of the incident laser frequency. So it is basically exciting the lower hybrid waves, disturbances. If you look at the energy absorption, again, you can, these red lines are for ions and the blue lines here, not these ones, the green lines here and here are for electrons. And this is the dashed line is for the case when there is no magnetic field. So if you compare electron energy, it was higher in the absence of magnetic field, ion was very low. Whereas if in the presence of strong magnetic field, the ion energy shot up and the electron energy has reduced. So we have achieved what we wanted. The energy distribution for the two cases here, electron energies are higher. Here, on the other hand, the ions with the magnetic field, the ion energies at various times are increasing. Momentum space distribution also. There's a preference of higher values of ion energy. And we also carried out with the finite laser spot size, there were no differences. And how do we understand it? In fact, if you look at in the presence of applied magnetic field, there will be a E cross B kind of drift. B is B naught applied magnetic field. For a static E cross B drift for electrons and ions, the drift is similar. But when you have an oscillating electric field and B naught is constant, then this factor comes in. So it is different for electrons and ions. And E also has a dependence with respect to K. So the direction of this drift is along X. The wave number is along X. So this has a divergence, you have a divergence of V, which generates current. If you calculate the current is not zero, so there's a divergence of that. And so that generates charge separation. And this is the charge separation which is responsible for the generation of electrostatic fields, which we have shown here also. Sorry. For different values of B field, when B is 0, electron and ion densities are similar. As you increase the B, the differences increase. But when B is very large, then this can be ignored. And again, they try to acquire similar densities. So it's only at intermediate value of B that you have the maximum charge separation. We also did the theoretical fit of the velocity. And you can see the electrons exactly match with you can take it from the experiment, the E and B values, and then evaluate the velocity of electrons. And the theoretical and simulation fit match. For ions, on the other hand, it matches with this. There is a EX that gets generated, and this is VX matches with this particular value. There's a phase difference, as you can see, which will happen because dVx by dt. There should be I also there. And energy absorption maximizes as an intermediate B, because here at lower fields as well as higher fields, there's no electrostatic wave generation. So these are, we also made possible the localized heating by having a profile for the magnetic field. And you can see this is the time axis. that as the electromagnetic energy reduces, the electrostatic energy increases and the particle energy picks up. There are other like parametric processes, etc. We did things with that. And let me skip. Now, I'll just talk about. Just I wind up with 2-3 slides. Yeah. So the last results that I mean, like wanted to discuss about the transparency of the plasma. So that is what I'm coming to. And so here we carried out different geometries and so on. And you can see if you have a magnetic field which is stronger so that even the ions are magnetized, in that case, this is what you observe. So this is the plasma boundary in these two cases. Weak magnetic field, strong magnetic field, and this is vacuum propagation. Here, this was a RL mode geometry where magnetic field was parallel to the propagation direction. So it broke up into two waves, slow and fast waves. For a weak magnetic field, this is a strong magnetic field, and you can see, compare it with the vacuum propagation, identical. Nothing changes. And even at the other end, here you will see disturbances, but there will not be any disturbances here. So this I have shifted. You can see just like the vacuum propagation, it comes out. We did for finite laser spots also. This is a X mode. Now, X mode, if you have a finite laser spot size, it has both EY and EX. And this is the plot of EY and EX fields, and this is the plasma slab. In Osiris, it has to be placed, the laser roll always comes normal, so the slab has to be oriented. You can see that the X mode, the magnetic field is normal to the electric field, both the electric fields. So it will propagate, even though it is a finite spot size, it will be, nothing happens here. The plasma density doesn't change. It just goes at very strong magnetic field and it comes up. Is in the RL mode, there will be one component of the EX component parallel to the magnetic field. So that along propagation direction, you will see that this gets affected along this and electric field being in that direction. But this component still like a vacuum propagation, and there are different. So E cross B at high magnetic field is same. So there's no J that gets generated. But then for finite spot size, one would feel that quantum forces made difference. So for the magnetized case, we carried out the unmagnetized case. You can see there's a mass dependence on force. So electron and ions will move differently. But if you take a X mode and R mode geometry for a magnetized case, then you can see this alpha is a polarization. So alpha equal to 0 is basically the X mode. Otherwise, there will be a combination of O and X mode. So here you can see that when this is very high, the cyclotron frequencies compared to the laser frequency, this one can be ignored and mass term gets cancelled away and you get the same value of ponderomotive force. And so that's what it is all about. So clearly there's a possibility of complete transmission emissions. And it's a new mechanism. What is happening is that even though the ions are moving, but J is 0 here, and that is what is giving rise to transparency. And let me now acknowledge, this is my acknowledgements. Thank you. Any questions? I'll be.
Questions?
You discussed shocks, shock separation, etc. And at no point I was expecting reduction of the
I didn't get it.
You never discussed any effect. Even though you have shocks, you have shock separation. Obviously, you can have it in the free context or with a reduced size ratio that will help the genetic context. Especially with the things, compression, etc. Really affect to modify the dynamics of the iron.
This, you are saying that there will be electrostatic fields that will get generated in the shock region. Okay.
You wrote down an equation, a classical equation for a collisional shock, right? Why
Yeah.
isn't it a collisional shock?
I mean, like collision term is not affecting it.
No, but the question is, he's asking, what's the relevant scale? Is it in a collisional shock, the scale is the mean free path. In a collisional shock, the scale is going to be set by the Debye length or some other thing like that. In other words, why the collisional regime assumption? And the question of you may get off the hook by saying you don't care about that, but you have to demonstrate that.
What I'm saying is that as long as dissipation is present, no matter by what it is coming, it doesn't affect.
But I mean, you didn't demonstrate that, right?
What kind of demonstration?
You should.
The PIC simulations, okay.
No, but wait a second. I think he's got you. I think the point is that it may not be dissipative. It's dispersive. In a collisionless shock, you limit steepening by dispersion, not dissipation. So it becomes a question of comparing the dissipation scale and the dispersion scale.
Yeah,
it's a fair point.
So the skin depth is a dispersive scale.
Yeah, but I mean, the question, if that becomes shorter than the dissipation scale, then that becomes the relevant scale in the problem.
Yeah, the scales are shorter than the electron skin depth. And that is why the Kelvin-Helmholtz instabilities and others develop. If you look at the PIC simulations, there those instabilities, they come in. That was an approximation. Yeah, so actually, I mean, like, it's not that I've written Burger's equation out of the blue. If you look at the generalized electron magnetohydrodynamic equations, they reduce to Burger's equation. And even if they don't reduce, you can have B minus del square B terms. And for the entire equation, we have evolved. Okay. So in the derivation of the electron magnetohydrodynamic model, one assumes that there is no electrostatic fields, even if they are, by taking the curl, they have gone away. So one assumes that in the derivation of electron magnetohydrodynamic medium. And there the time scales are assumed where you ignore the displacement current. So that approximation in the fluid model is there. But when I do a PIC simulation, everything is there. Right? All the things are there, and that was demonstrated using PIC simulations also.
The put it charitably, the equation you wrote then need not have any relation to what went on in the simulation.
No, in some limit, the GE-MHD equations can be
No, but not
reduced to.
with the resistivity. If
What?
the shock is collisionless, the thing on the right-hand side is the diffusion.
This
It's
is
a
okay.
dispersion.
This
That's
is
the point. What's
this-
the relevant scale on the right-hand side? Why don't we, I
Okay.
think we're going in circles
Okay,
here.
okay.
Any other questions? Anything else? All right, let's thank Amita again.
Thank you.